Hi, it's Jennifer Hawkshorse, and we're going to continue with Chapter 4 on multiple integration in this video. So we're a couple sections deep into this chapter. We've already talked about double integrals over rectangular regions. Then we went over double integrals over more general regions. And now in this section, we're going to look at double integrals over polar regions. So our goal for this section is to be able to write and evaluate double integrals in polar coordinates. All right, so polar coordinates is something we discussed back in Calc 2, and then we also reviewed it in section 1.7 of Calc 3. This was the theorem I had given you, and this is how we would convert back and forth between the two coordinates. So polar coordinates, those ordered pairs, they're written as r theta. Rectangular coordinates, those are written as x, y, and if we go and convert from polar to rectangular, we would use these two equations right here. X is equal to r cosine theta, y is equal to r sine theta. And if we were converting from rectangular to polar, we were using tangent theta equals y over x, and r squared equals x squared plus y squared. So we're already familiar with these, so this is like a review. All right, so polar regions. Suppose we want to evaluate a double integral like this over region R, where R is one of these regions below. All right, if I wanted to go and describe R in terms of rectangular coordinates, it would get really, really messy. It's rather complicated. But if I take that same region R and I describe it using polar coordinates, it's actually quite easy. So what we're going to do for some of the examples, I will have us set up the double integrals, the iterated integrals using rectangular coordinates and polar coordinates, and we'll see that for regions like these here, pictured here, polar coordinates ends up being easier to work with. All right, so polar regions. These regions are basically special cases of polar sectors, or some textbooks call them polar rectangles. So a regular rectangle, it looks like this. A polar rectangle is this shape over here. I'm going to kind of copy it over on the side, and I'm going to exaggerate it a little bit. But two of the ends are arced, like this. These two are straight, but one end is like larger than the other. All right, so that is a polar rectangle or a polar sector. All right, so these regions are special cases of those. Now I will bring up the polar sectors again in a couple slides from now, when I get into the integration. But for now, let's just do a quick example where we go ahead and we describe regions like these using polar coordinates. So what we'll do is we'll say R is equal to all ordered pair R theta, such that R is between two radii and theta is between two angles. All right, so we're going to use basically this set notation. So this is the first example. Just use polar coordinates to describe these regions. And I'm giving you the curves here in rectangular form so you can see that you're already getting a little complicated. Going to work on the next, this slide here, we'll put my answer. All right, there's example 1, part A. All right, so basically, if I'm using this here, I just need to figure out what's R between and what's theta between. All right, so R is between 2 and 3, right? Because you have radius 2 and then you have radius 3, right? This is like 2 squared, this is like 3 squared. All right, so I know what R is between. Oops. All right. So region R is a set of all ordered pair, R theta, such that R is between 2 and 3. And now I got to figure out what's theta between. All right, so theta goes from 0, that angle, all the way over here, which is pi. So 0 to pi. All right, so that's all you have to do for describing that region in polar coordinates. Let's do part B. So this is going to be the set of all ordered pairs, r theta, such that r goes from 0 to 2, and theta goes from 0 to 2 pi. Okay, so r goes from 0 to 2, and theta is between, oops, that's theta there, between 0 and 2 pi. Okay, so that's all you have to do for describing the regions. Now we're going to go back into the integration. All right, so double integrals in polar coordinates. So if we want to define a double integral of a continuous function in polar coordinates, consider the region R, that's below, pictured below, which is bounded by the graphs of R equals G sub 1 and R equals G sub 2, and the lines theta equals alpha and beta. All right, so G sub 1 is this curve here. Oops. G sub 2 is this curve here. And then this is alpha, this line. And this is beta, this line. All right, so those 4 things basically bound our region R. So this area in here, that's our region R. Okay. All right. Instead of partitioning that region R into small rectangles, like we did back in section 4.1, basically we had a region. We were working with the rectangular region, so we broke it up into smaller rectangles. When you have a region that's like this one here, you're actually going to partition it into small polar sectors. So if you bring one of these sectors out, it's going to look something like this, right? If you're looking at it up close. Okay, so basically think of taking region R and superimposing a polar grid on it. All right, so we break up this region into polar sectors. All right, so back in the first section for this chapter, 4.1, to find basically the area of this region here, we would sum up the area of each of these rectangles. So we want to do that same concept here in this section, except in order to find this area, we have to sum up the area of all these little polar sectors. So let's figure out what the area of a polar sector is. So the area of a specific polar section is given by this here. Delta A is equal to R, delta theta. Delta theta is a small change in the angle, and delta R is that small change in the radius. Now notice you have an extra factor of R here, and that is that's because of the arc length for a circle is R theta. So you have the extra factor there. Now the volume of a solid region of height given by basically f of x, y, except in polar coordinates that would be r cosine theta, r sine theta, is given by this here. So this is the volume. Basically it's the height times the area of the polar sector. So we have that this double integral can be rewritten this way. So instead of f of xy, you'll have f of r cosine theta, r sine theta, and instead of dA, you will have r dr d theta. Don't forget this extra factor of r. Sometimes students forget that. Now the limits of integration, these here, those can be functions in terms of theta because that's the outside differential, and alpha and beta would be constants. All right, there's a picture up close if you need it. All right, theorem here for the change of variables to polar form. All right, so this is a theorem we're going to use when we go ahead and we convert to polar equations, polar coordinates. So we're going to let R here be a plane region consisting of points x, y, which are equal to r cosine theta, r sine theta, satisfying these conditions. Now, this first condition basically says that your radius is between these two curves, and they're also not negative. And theta is between these two angles here, where the difference in those two angles is somewhere between 0 and 2 pi. If G sub 1 and G sub 2 are continuous on the interval from alpha to beta, and f is continuous on that region, then you can take your double integral and set it up this way. So that's what we're going to use. All right, so for example 2, we finally made to an integral problem. We want to evaluate this iterated integral by converting it to polar coordinates. And we also want to sketch the plane region. So maybe not the three-dimensional picture, but at least sketch the plane region. All right, and you can kind of see too, looking at this as it is, look how complicated it is. You have the composition function inside and outside. You've got like roots and the limits of integration. This would be a mess to try to integrate. So maybe when we convert it to polar coordinates, it'll be easier and we can actually finish integrating it. So I'm just going to copy this onto the next slide so we have a little bit more room. Right. So it's -1 to 1, 0 to square root 1 minus x squared. And then it was y x squared plus y squared to 3/2 power dy dx. All right, so that's what we're working with. So the first thing I'm going to do is I'm going to sketch the region. All right, so just in the x, y plane. It's a little cricket, sorry about that. Okay, so let's see. Y is going from -1 to 1. I'm just going to mark that down. -1. Oops, I'm sorry, that's the x, excuse me. X is going from -1 to 1. So I'm marking that down. And y is between 0 and this square root thing. So that square root thing is the upper half of the circle with radius 1, and it's centered at 0. Something like that. All right, so you can just say y equals this, plug in your graphing calculator. Okay, so it looks like that. So these limits of integration there, they give us the region, but I want to rewrite the region so that, and I should label this R, so that I'm using polar coordinates. All right, so that's what I'm going to do. I'm going to switch those integrals, those limits of integration to the polar. All right, so I will leave a little space here for the integrand, and this here, that's like the dA, that turns into R dr d theta. Okay, all right, so R is going from 0 to 1, right? Because we go from 0 to 1, that's the radius. And then theta, the angle, is going from 0 to pi. So you can have 0 to pi. All right, that gives us basically that top half of a circle that's centered at 0, that has radius 1. All right, now I have to figure out how do I take this integrand here and convert that over. So you could do some scratch work on the side if you have to. Y, I know that's equal to r sine theta, so I'll just write that down. But this part in the parentheses, let me just make a note over here. So you have x squared plus y squared to 3/2. Well, using your conversions, x squared plus r squared, x squared plus y squared is r squared. And then when you simplify the exponents, you just get r cubed. Okay, so there's an r cubed there. All right, let's clean this up a little bit more. So we're going from 0 to pi, 0 to 1, and then we've got sine theta, and then we have r to the 5th, right? Because there's this r cubed, and there's this r, dr d theta. Okay, so we went from, this thing here, which I wouldn't even want to start to integrate, to this thing over here, which is a lot easier. Plus, all your limits of integration are constants now, which is nice too. All right, so let's go ahead and actually finish this, and we'll do that on the next slide. So we're going from 0 to pi, 0 to 1, sine theta, r to the 5th, dr d theta. All right, so we go ahead, we're going to integrate, we're going to work our way from like the inside out. So we're taking care of this first integral inside here, and we're integrating with respect to r, so theta here is treated like a constant. So you're going to have sine theta, r to the 6, divide somewhere by 6, I'll put like a 1/6 in the front there, and we are going from 0 to 1, and you still have the d theta. Okay, so we're still integrating 0 to pi, and then we're going to plug in the upper limit 1 minus plug in the lower limit 0. Okay, and then clean this up. All right, so now I just have 1/6 sine and sine theta, and I'm integrating with respect to theta now. So it's just like a Calc 1 thing. So the antiderivative of sine would be negative cosine. And we'll go from 0 to pi. All right, so you get negative 1/6 cosine pi minus cosine 0. Cosine pi, negative 1. Cosine 0, plus 1. I'm trying to write this a little bit smaller. So this is negative 2 times negative 1/6. That's positive 1/3. So that's your answer. So that actually wasn't so bad to integrate. But I wouldn't want to go and integrate it the way it was set up first, originally. That looks like a mess. All right, but this wasn't too bad. So you got 1/3 as your answer. All right, let's try this again. So we're going to use polar coordinates again to evaluate the double integral. We want to sketch the plane region like we did in the last example. So we have this double integral over region R, and here region R, let's see, R is the region that lies between these two circles in the first quadrant. All right, so we'll sketch that on the next slide. Copy the stuff over. All right, so example 3. All right, so we're going from, let's see, we're going over region R. We've got e to the negative x squared minus y squared dA. All right, so R here is supposed to be between two curves, right, two circles. So this has radius 1, this has radius square root 2, and we're in the first quadrant. Okay, so we're in this, did I say quadrant? Yeah. So we're in this first quadrant right here, and you have a circle with radius 1, and then another circle, radius square root 2. So this here is your region, right there. That looks like a slinky. That's not supposed to do that. All right, there, that's better. All right, so go ahead over here. I'm going to leave the integral in for now. This part here, dA, that gets replaced with r dr d theta. Then I'm going to take care of the limits of integration. So r is going from 1 to square root 2, right? Radius 1 to radius square root 2. And theta is going from 0 to pi over 2, if I'm going to stay in that first quadrant. All right, and then this exponent, let's make a note here. The exponent on e is negative x squared minus y squared. That's the same as negative x squared plus y squared, which is negative r squared. So then I'm going to have e to negative r squared power. All right, so I've converted to polar coordinates, and now I want to figure out how I can integrate this. All right, so let me switch colors here. All right, so I want to do the inside first and work my way out. All right, so I'm going to write like a little note here. I'm going to keep it in a different color. If I'm just looking at this part here, right, ignore the limits of integration. We're going to do some scratch work. You can use u sub to integrate this, where u would be equal to the exponent, negative r squared, and then du is equal to negative 2r dr. So you have your r, you have your dr. You're missing the negative 2 though, but you can fix that. Use a different color. So you can multiply the inside by a negative 2 as long as you divide somewhere by a negative 2. All right, so the negative 2, the r, the dr, all of that gets replaced with du. Negative 1/2 integral I would have du, and then I would have e to the u power, because u is what I said set equal to negative r squared. All right, so this is really jammed in there, but you get the idea. All right, then you would integrate this, you get negative 1/2 e to the u plus c, right? Which is the same as negative 1/2 e to the negative r squared plus c. All right, that's my scratch work. That's going to help me integrate this, which I'm going to continue on the next slide. All right, so that's the scratch work. So we're going from 0, pi over 2, 0, oop, no, that's 1, square root 2, oops, clean that up. So this is equal to 0, pi over 2, that integral. When I integrate this, that gave me negative 1/2 e to negative r squared, and we're going from 1 to square root 2, and you still have a d theta. All right, so this is equal to integral from 0 to pi over 2. Then we have to plug in the upper limit, square root 2, minus plug in the lower limit 1. Maybe simplify this a little bit. Okay, now there's no r's left, there's no thetas, right? So this is just a constant. Now we're going to integrate with respect to theta. So we're going to get just negative 1/2 e to the negative 2 minus e to the negative 1 theta, and theta is going from 0 to pi over 2. So this is going to give us that, which I don't really want to leave like that. Can I simplify this? I'm going to write this as pi over 4 e to the negative 1 minus e to the negative 2. Distribute that negative through and rearrange the terms in the parentheses. So you can leave it like that, or if the negative exponents bother you, you can write it this way too. Anyway, that's your answer. And again, the integration wasn't so bad once we converted it. All right, so example 4, use a double integral in polar coordinates to find the volume of the solid region that lies under the surface of this thing and above the circle of this thing in the xy plane. Sketch the solid region and the plane region. So let's try this. So example 4. All right, so it's supposed to be below z equals x squared plus y squared plus 2. That's a paraboloid. We talked about that in chapter 1. And it's supposed to be above x squared plus y squared equals 16, above that circle in the xy plane. So let's see what the picture of this would look like. This is x, y, z. So here you have your circle. That's this thing right here. So this it's centered at 0, 0, and has radius 4. Okay, and it's in the xy plane. And then this surface, that's your paraboloid that's been shifted up a couple units because it's got a +2 here at the end. It looks something like this, right? And it goes up. All right, and then since we're trying to find the volume between that and the circle in the xy plane, basically, get another color. This is our shape here, though. So basically, it looks like a cylinder, right? But it's got like this dip in it from that paraboloid shape. Right, something like that. So this part has been like scooped out. All right, so we need to find the volume of that thing. And I'm going to also go ahead and draw the region. So that's the solid, right, what we're trying to find the volume of. And then the region is just basically this part here. So just the circle centered at 0, 0 was radius 4. All right, so I need to find the volume. So the volume is going to be equal to the double integral over this region R of the function dA. Okay, so in polar coordinates, I gotta figure out what this function is going to be. All right, so the function f of x, y, that would be the surface here, given by this. So in polar coordinates, this x squared, y squared would get replaced with r squared. All right, so that's going to be my function. That's going in here. That's the integral. And then the dA gets turned into r dr d theta. And then in polar coordinates, my limits, gotta adjust those. So for r, we're going from 0 to 4. And theta, we're making a complete circle. So that would be 0 to 2 pi. All right, so we've set it up, so I'm going to go ahead and actually evaluate it on the next slide. Okay, so I'm going to take this r here and distribute it through. So we have r cubed plus 2r dr d theta. And I'm going to go ahead and integrate that with respect to r. So I'm going to get 1/4 r to the 4th plus r squared. And we're going from 0 to 4 d theta. Okay, so I'm going to plug in the upper limit 4. So when I plug that in, I'm going to get 64 plus 16. And then minus, plug in the lower limit 0, which is just 0, so I'm not going to worry about that. So it looks like I'm going from 0 to 2 pi. 64 plus 16, so I just got 80 d theta. So I'm integrating with respect to theta, so it's just 80 theta, and we're going from 0 to 2 pi. Plug in the upper limit. 80 times 2 pi is 160 pi. That's your answer. Plug in 0, you just get 0. So your answer, that volume, is 160 pi. And that's it. That's all you have to do for this problem. All right, there's one more thing we want to go over, and we kind of did something similar to this in the other sections already. But if A, B, C, and D, if they are all constants, right, and G of R and H of theta are separable, then you can take this here, double integral, and write it as the product of two single integrals. So we already did something like this in the previous section. We'll do one example like this, and I think we'll be done with 4.3. All right, example 5, we want to evaluate the iterated integral by writing it as a product of single integrals. All right, so we're going to have one single integral times another one. All right, so the first one's going to go from 0 to pi, and these are the outer limits of integration, right? So that's going to go, that has to do with the theta. There's no theta there, so I'm just going to put 1 d theta. And then the other single integral is going to go from 0 to 1. And this is for r. And you have an r to the 4th dr. There you go. So you can separate the r's and the thetas, really. All right. So integrate this. That's just theta going from 0 to pi. And integrate this. That's 1/5 r to the 5th going from 0 to 1. So you get pi times 1/5, pi fifth. And that's your answer. There's nothing else you have to do for that one. All right, try the homework. This section wasn't so bad. And then we're done with this. Thanks for listening.